Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome here, and thanks for showing up at this short notice. And in fact, yeah, we have more than the room capacity now. Thanks. Today our speaker is Vijay Vazirani. He's a professor in Georgia Tech, and he'll be presenting a talk on new market models and algorithms. And few words about Vijay. One thing, Vijay is my PhD advisor. Thanks. And he has written a popular book on approximation algorithms, which has been translated into a quarter dozen languages. So I didn't want to say 3.
Thank you. I'm sure everybody can do their arithmetic around here. So, yeah, it's a great honor to be here with such a distinguished company. Yeah, so I'm going to talk about markets. Should I close that door? That's legal, right? So the notion of markets has been around with us since ancient times. But as you all know, the notion has undergone dramatic changes through the ages. One of the big changes happened when stock markets were introduced. In particular, within these markets, you could sell something that you never owned. The only thing is you have to buy it back later at some time. So, bizarre markets like that got introduced, which completely are counterintuitive to our understanding of the ancient notion of a market. With the internet, again, the notion of a market went through a revolutionary definition. Totally new markets got defined by companies such as Google, Amazon, Yahoo, and eBay. And these markets, in fact, form a good fraction of the economy today, and are gradually growing and are expected to become an even larger player in the economy in the coming 10 years or so. The other big change is that we have at our disposal massive computational power available for running these markets either in a centralized or a distributed manner. And with all of these changes, it's become really critically important to find good algorithms for these markets and good models for modeling these new markets. And fortunately, the theory of algorithms has developed some very powerful tools over the last 4 decades, and we can count on many of these to help us with this new endeavor. The very interesting and exciting part for me is that there's also traffic in the reverse direction. Namely, the study of markets has contributed in a big way to this theory of algorithms as well. And I'll be highlighting these contributions whenever they come up. For me, that's, in some sense, the most exciting aspect of this work. But of course, all of the other important aspects are also holding. So I'm going to start with introducing you to or not introducing, but most people here are familiar with this. In Microsoft are familiar with this new market, the AdWords market. But there are lots of visitors here. So should I be introducing this market? How many people have no clue about this market? Really, otherwise, okay, so I need to say a bit about it. Okay, so, but sorry? Maybe about one bit. Okay, a few bits about it. Apparently the theory group here has a lot to do with this market. They know it much more than I do. But for the rest, let me just say a small introduction. So these markets are run by search engine companies such as Google, Yahoo, and MSN. And it's really a huge market, a multi-billion-dollar market, which really supports almost all of Google in terms of revenue and profits, a large percentage of Yahoo, and a good percentage also of MSN. This is not only a huge market in the sense that it supports this free search that we have available at our desktops, 24/7, and we keep using all the time, but also it has revolutionized advertising because it's given a venue for small advertisers to pitch in for themselves. Before this, only big advertisers could go out and advertise in TV and newspapers, but that takes a lot of money, obviously. So the way it works is that if you type in a search word such as Lunesta, which is a sleep-inducing new sleep-inducing drug, you get not only pages relevant to Lunesta, but also sponsored links either to these drug companies, the online pharmaceutical companies, or like these people, they want to cure your insomnia for $23.95 only, and it's been proven at Harvard Med School, for instance, and so on. So these people have actually bid. Sorry? eBay is always there, yeah, as we saw from Raghavan's talk. So yeah, so these advertisers have bid anywhere between 5 cents and $100 to be out there. And every time you click into one of these places, say here, then whatever they bid or some function of that goes from this company to Google and forms Google's revenue, right? And in this case, I mean, since they're only charging $23.95, they probably have bid only 5 cents to be there. But if you type in Vioxx, then you don't get pharmaceutical companies here. You get lawyers who want to attract the attention of people who are almost on the verge of dying because of Vioxx drugs that they took, and who can make these lawyers millions of dollars. So these people have actually bid somewhere on the range of $100 to be here. So every time you click here, $100 goes from this lawyer to Google's account. Okay. So in case there are some Google stock owners here, you know what to do in your spare time.
So you're suggesting that the lawyer should pay the 5 cents and get on the domestic account in advance?
How will that help them?
Well, just give it a little time.
Oh, in advance, okay. Oh, yeah. Yeah, but when it comes time to cash in, that's what will be $100. So anyway, so if you go to this site on Google, you can learn how it all works. You can set up an account for yourself for only $5. You can put in your favorite keywords and your ad and specify your daily budget. How much can Google charge you for a day of these search results? And it all works. There are, because of the power law phenomena, the tail of advertisers versus budgets that they have is very, very fat, and there are lots and hundreds of thousands of little advertisers, and it all adds up to being a lot of revenue for Google, of course. So in this context, in 2004, Monika Henzinger, who was then the CTO of Google, she posed this question of finding an online algorithm to maximize Google's revenue. Okay, sorry.
I said Google must like that goal.
Oh yeah, and in fact, yeah. So let me be more specific about the exact problem that she posed, because it's not exactly the way Google works, but it's a simplification, but something that can be analyzed theoretically. So let me just say the model that she had proposed to us. So suppose there are n advertisers, and they have daily budgets of B1 through Bn, all specified, and they have made bids for some keywords. All of their bids and keywords are specified, an advertiser can have different bids for different keywords and a single daily budget for all of the keywords. Okay, and the job of the search engine is that as queries come online, the search engine, like say Google, has to select who to one advertiser. So here on the side of this, we saw many ads, but let's say that only one advertiser is to be chosen for simplicity. Can be changed later very easily. So let's say only one advertiser needs to be chosen, and let's say that this advertiser pays his bid to Google at that point. Okay. So, and in this online setting, we want to maximize Google's revenue, and so the obvious thing we use is online competitive analysis, which means that we'll compare the performance of our algorithm with that of the best offline algorithm, which knows all the queries in advance. Okay. So one simple algorithm, of course, is to simply give this query to the highest bidder who still has money left over, right? And it's easy to see that can get half of the offline revenue, but can be stuck at exactly half. So let me run an example which will also clarify the whole model. So suppose there are two bidders here, bidder 1 and 2, and bidder 1 has bid $1 for every book query that he gets and $1 for every CD query that he gets. And bidder 2 has bid 99 cents for book queries and not interested in CD queries. Okay, and suppose that today 100 book queries are going to come first, and then 100 CD queries are going to come. Okay, so let's see what happens if we run the greedy algorithm. So when a book query comes, between these two bidders, obviously it should go to the first bidder, right, for $1. And in fact, all these 100 queries should go to the first bidder, and his money is fully used up, his $100. Oh, by the way, B1 and B2 both have $100 each for today. So B1's money is fully used up, and so when the CD queries come, well, bidder 2 is not interested, bidder 1 has no money, so they all go wasted, right? Whereas the optimal thing, so then you get a revenue of $100, but of course the optimal thing to do was to send all the book queries to bidder 2 for $99 and all the CD queries to bidder 1 for $100 for a total of $199. So you're stuck with about half the revenue, right? So how should we do better than this trivial greedy algorithm? So turns out that we can draw on our beautiful theory of algorithms and find some rather interesting results there. And the way to do that is to notice that this problem is simply a generalization of online bipartite matching, in which in this special case, each daily budget is $1 for each advertiser, and each bid is either $0 or $1. Okay, so let's see why. So suppose there are these 5 advertisers coming to the market with $1 each, and they have bid on some of these queries. Different people have bid on these queries, $1 or $0. So when a query comes, let's say that we put edges to all the advertisers that have bid $1 for this query, and we assign this query to one of these advertisers. And the next query comes, we assign to another guy, and use up the $1. After that, this advertiser has no money. So we'll be finding a matching in this way, right? It's online matching. So these are the boys sitting here. The girls come one at a time together with all their edges, and you have to match off the girls right away, online. You don't know what the preferences for the next girls are going to be, right? If you know all of that, you'll just run a maximum matching algorithm. But how well do you do online? And turns out that you can do 1 minus 1 over E online with a randomized algorithm. This was an ancient result when there were no ulterior motives for this work. And this is an optimal algorithm, moreover. And there's another very nice result, that of Kalyan Sundaram and Pruz from '96, showing that for the B matching problem, which is that every advertiser has a daily budget of $B, but the bids are still 0 or 1, and B is very large compared to 1. even then they can get 1 minus 1 over E factor algorithm, but this one is deterministic. Okay, and last year we managed to get the same factor for the AdWords problem, assuming that the bids are much larger than the budgets. And the interesting thing in our algorithm, and this is optimal, and the interesting thing in our algorithm is that we use not only the bid, but also the fraction of leftover budget of each advertiser to decide who gets the next query. Okay, and the exact manner in which the bid and the fraction of leftover budget are traded off is decided through a function that is obtained through a new technique called the trade-off revealing family of LPs in a rather magical way. And the reason I say magical way is that we still don't understand the full scope of this particular technique. This is an infinite family of infinite family of LPs whose right-hand sides magically give you the right trade-off function between bid and fraction of leftover budget. So this is what I mean, that the study of these markets is feeding back into the theory of algorithms in a very interesting way. So this was a little aside just to show you that there are totally new markets out there, totally different from any markets that we knew of before. Okay, and we do need new models and algorithms for these markets. But my main talk is about market equilibria, and the study of market equilibria has been a very sort of a big theme in the West because our economy is capitalistic, and so pricing mechanisms determine everything. There's no intervention at all in saying what gets priced more. The market decides all the prices. There's no all pervasive, benevolent, and very smart central authority that's saying you get more money than this, or this is more expensive than this. Everything is being decided by the market, and the issue is do these pricing mechanisms at least have inherent stability in them or not? Are we going to be cycling through prices and always being unstable? Is there efficiency? So where goods and services are needed to produce important things, do they reach there or not? Is there fairness in the market? Is it the case that some people get very, very rich and some people don't have anything to live on? So these are important questions, and do pricing mechanisms have these inherent properties or not? Right. So this was a very big issue in mathematical economics, and in particular, do markets even have stable operating points? This was, in fact, the central question within general equilibrium theory, which which is really the crown jewel of mathematical economics, and I'll show you how important it was as for over a century, basically. So let me give you a very brief historical introduction to this general equilibrium theory. So this theory was pioneered by Leon Walras, a French mathematician, economist rather, and he gave some very critical fundamental models for this theory. So suppose there's only one good. Okay, then what's the equilibrium price? At what price should this good be sold? Well, there are these well-known demand and supply curves. So as the price goes lower, the demand goes higher, and the supply drops. Right? The demand goes higher and the supply drops as the price goes lower, obviously. Right? If the price increases, people will want to produce more of that good because they'll earn more profits. So wherever the supply and demand curves meet, that's the equilibrium price. Because imagine if you are operating below this, then demand is bigger than supply, and people are ready to pay more and more. They don't get enough of this good, and so soon the prices will go up to equilibrium. Or if prices are too high, then there's surplus supply, and there's a lot of excess of this good in the market, and so the suppliers will soon cut back, and prices will keep dropping until they hit equilibrium again. So that's the case of the single good. But how do you even formalize the notion of equilibrium prices for the case of multiple goods? Just formalizing this question is not straightforward. So let me show you a very interesting formalization due to Irving Fisher, who was a PhD student in the economics department at Yale in finishing off in 1891, and he gave this fundamental market model that's being studied even today very extensively. In fact, most of the rest of this talk is based on his model. And here's the model. So suppose that there's a market with a bunch of divisible goods like bread, cheese, wine, milk. Okay. And some people come to this market, and you might recognize some of these people. And they have different amounts of money that they want to spend in this market, and even the silly professor has some few cents to spend. And given any prices of these goods, each one wants to maximize their happiness. So they let's assume that they have linear utilities, and I'll formalize that in a moment. But if you set the prices of these goods at any given values, each one says, okay, how do I best spend the money that I brought to this market, right? And so that my utility is maximized. Okay. Oh, it becomes louder like that. It's better, right? Okay. So they go out and they oops. Okay. I don't know what to do with that. They go out okay, they go out and buy their optimal bundles of goods. And the issue is, can you find prices so that even though everybody gets their optimal bundle, the market clears exactly? Which means that all the money gets spent and all the goods get bought down to the last drop. So there's no deficiency or supply of any good. Okay, so this is kind of, you can see that demand equals supply happens at these prices. Okay, so are there such prices in a market with multiple goods and people with different utilities, right? So Fisher, who gave this model for his PhD thesis, so here's the formulation for Fisher's model. So fully mathematically specified now. So suppose there are n buyers, each coming with some money mi. There are k goods, and we can assume unit amount of each good without loss of generality. And say that buyer I derives uij amount of happiness if she gets 1 unit of good j. Right? So if she gets xij units of good j, where xij's are between 0 and 1, then this is the total happiness that buyer I derives. And this is what I mean by linear utilities. That happiness linearly depends on the amounts of goods. So if this function were quadratic or logarithmic or something, that would be some other utility functions. And so again, the issue is you want to find prices so that the market clears, so that all goods are sold and all money is spent. So after giving this model, Fisher was also in those days worried about the computational aspects, and he didn't give a mathematical solution, but he gave this hydraulic apparatus in which there are these levers and these cisterns of different shapes depending on the utility functions of these buyers. And this is the case of 3 goods and 3 people. And once you fill it with water up to a certain level and let the levers settle, then you can read off the prices from the levers. So that works. Sorry?
So there's nothing in the model that says that, say, Bill Gates is sad to lose his money, to spend his money.
Huh?
That people are not sad. People are not upset to spend all their money.
No, they came to the market to spend all their money.
Okay.
They have many more money in the bank, you know.
Okay.
This was the money they came to the market to spend.
I thought we were breaking up all zero everything. Okay, good.
So actually, this device is quite impressive. There's a copy of this in the economics department at Yale, and in fact, a few years ago, Herb Scarf, who's a very distinguished professor at that department, tried to build this device with his graduate students, and modern technology didn't allow him to. So it all failed, and then later he asked his graduate students to simulate this on a computer, and it worked. And there's even a paper on his homepage saying how to compute equilibrium prices in 1891. Okay, so the computational aspect is important. Okay, going from Fisher's model, the big theorem, of course, here in this whole field is the Arrow-Debreu theorem, which was proven in 1954. And it's really a celebrated theorem. It established the existence of equilibrium prices in a very general setting, even more general than Fisher's setting, in actually Walras's original setting. And it uses a deep theorem from topology, the Kakutani fixed point theorem. And in fact, for this theorem, Kenneth Arrow, who's a professor emeritus at Stanford, got a Nobel Prize in 1972, and Debreu, who was a professor at Berkeley and passed away a couple of years ago, got the prize in 83. So the trouble with this theorem, though, is that it's highly non-constructive because of the use of Kakutani's fixed point theorem. And in fact, this whole theory developed within mathematical economics has only a few isolated computational results. It's almost entirely just an existential theory. Typically, you know, over the years, okay. Let me say it another way. So suppose you ask an economist, you know, does the market really compute an equilibrium? Okay, but what they'll quote to you is this quote from Adam Smith's treatise, Wealth of Nations, that the invisible hand of the market does it, you know. But really, do they compute equilibria or not? Or even more fundamentally, can we even compute equilibria on a computer? Because if we can't compute it on a computer, then markets are certainly not computing them, right? So can these equilibria even be computed in polynomial time? So that's a fundamental question, right? Almost as fundamental as the existence question itself. So this kind of an answer, in the presence of the beautiful theory of algorithms that we have today, is not sufficient, and we need to really look for an algorithmic answer to this question. So that's what is needed today, is a different theory of market equilibria, an inherently algorithmic theory, unlike the previous one. And also, we need to think about new models that capture these new markets. So, fortunately, the beginnings of such a theory has started within algorithmic game theory, and it started with the design of combinatorial algorithms for these traditional market models of Fisher and Arrow-Debreu and Walras. And lately, new market models have been emerging, and my talk will concentrate on these new market models mainly. But let me just say that one of the first results in this whole business was a combinatorial polynomial time algorithm for Fisher's model, the one that I just stated. So in 2002 spring, I was on a sabbatic at Berkeley with my students Nikhil Devanur and Abhin Saberi, and together with Christos Papadimitriou, we obtained this polynomial time algorithm. And the interesting thing about it is that it uses the primal-dual schema, which, as you would know, is a very highly successful algorithmic design technique from exact and approximation algorithms. In fact, it was discovered in the context of bipartite matching by Kuhn in 1955. Yeah.
I pushed a bit on that. So you're saying that computers can't compute these market equilibria.
Yeah. Yeah.
Surely that's useless. If they exist, computers should be able to compute.
Or approximate equilibria at least.
You could make the same argument about quantum mechanics.
That
How to compute them on
on a quantum computer?
Well, on a quantum computer you can, but it's a different thing.
Yeah.
So maybe this
But there you have a quantum computer to compute it. Nature has.
Right, exactly. So maybe there's a native computer.
Oh my God. That would be no. Look, the church Turing thesis at this point at least has only one exception to it, that maybe quantum computers exist. Okay. Other than that, everything is classical, and by the church Turing thesis, everything that can be ever computed in any computing device of any kind should be computable on a Turing machine, which means all you need is an infinite roll of toilet paper and a pencil to write on the squares. Okay. So if you cannot do that, then no market should be able to do that. No other computing device should be able to do that. Okay. So basically, this schema, as I said, was discovered by Kuhn in 1955, and he called it the Hungarian method. In regard for the Hungarian combinators who had been studying matching for many decades before that. And actually last year, in 2005, they celebrated the 50th anniversary of this discovery in Budapest. So this method has given the most efficient known algorithms for all these fundamental problems in P, as well as many fundamental problems that are NP hard. It's given approximation algorithms with good running times and good approximation factors. So what's going on here is that we don't know of any LPs that capture equilibrium for Fisher's model. Okay, but there is a nonlinear convex program, a fantastic convex program due to Eisenberg and Gale with really beautiful properties, which captures equilibrium. So what I mean by that is that the optimal solution to this convex program is equilibrium allocations to Fisher's model. And our algorithm is actually solving this convex program via primal-dual approach exactly in polynomial time, though not strongly polynomial time. And that's an important question left over here. So we can do it in polynomial time, but not strongly polynomial time. So that's among the feedback, or rather the important contributions from the study of markets to the theory of algorithms. I think that's even bigger a deal than the one that I said earlier, and I'll show you more about this in the rest of the talk. So let's start with defining a combinatorial market, a new market. So suppose we have a network here with capacities on edges, and we have a bunch of source sink pairs. So S1 T1 and S2 T2, and there are capacities on edges, and let's say we also know the money that this source sink pair has and that this source sink pair has. Okay? Do we need a break for questions? No, everything's fine. Okay, so these source sink pairs have these monies, and the issue is to find equilibrium flows and prices, edge prices. Okay. So please feel free to stop me if you. Yeah. Yeah. Good.
You never mentioned the rate at which equilibrium is reached.
I said polynomial time.
I see. Okay. So,
You'll see more about it soon when we go through real algorithms.
but that has some practical implications on it, because in order to reach the equilibrium, you have to do certain things, right? In order to watch the market,
Well,
during the time, if something changes.
these are. Oh yeah. We're not doing dynamics of these markets. Yeah. Okay. So this is the model. We are given a network with vertices and edges, directed or undirected. We'll consider directed, and capacities on these edges, and a bunch of sourcing pairs with their monies. And we want to find equilibrium flows and edge prices. And what I mean by that is that we want to find the amount of flow that each SI sends to the TI, and the amount of price per unit flow of each edge, so that these equilibrium conditions are satisfied. Namely, an edge can have positive price only if it is saturated. If it is not fully saturated, it must have zero price. Every flow must go on a cheapest path from the source to the sink, and the money of each agent must be fully spent. Okay. So I just want to take a minute to be sure that you get this model, because everything now depends on this definition. So feel free to ask me questions. Yeah. Yes. These conditions? Well, these are natural. So for instance, okay, yeah. Let's think of the Fisher market. We could have said, okay, so any good that is not fully sold must have zero price. We could have said that. Instead of saying every good must be sold, okay, every good can be sold only if there's somebody out there who wants that good, who has non-zero utility for that good. So the more general statement to say is that a good must have zero price if it is not fully sold. So it can have positive price only if it is fully sold. The money of each agent is fully spent, right? And in this case, there's no business of going along cheapest paths. But I mean, why would, okay? So imagine.
They like they don't fully sell something, you still charge something.
Yeah, but that's I mean, so we are talking of.
This looks like complementary conditions that would later help you with that.
Of course, yeah. But this is also the correct model in economics, that things that are surplus must have zero price. There's not real demand for these things all the way to their being sold off completely.
Why? What if there's just limited money? What if you can start off with so much?
I'm sorry?
You might get price for some of them, make a visit to spending everything. I mean, you may just more oranges than people have money for, but you still get some money for some of them.
Look, this is a standard thing in economics that so we are just talking about this model of a market. We're not in the market with no oranges, yeah. Okay, so if I assign prices to these edges, what would a source sink want to do? Go along the get flow on the expensive path or the cheaper path? It wants to. Every source sink wants to maximize the flow that it got. Okay. Obviously, it wants flow along the cheapest path. Obviously, it wants to spend all its money, and obviously, where there are no bottlenecks, you cannot price it because it's not a useful edge. Until it becomes a bottleneck, until it becomes fully saturated, there's no reason to price it. Right? So it's completely natural. Okay. So this is in fact this particular model was given by Kelly in his very fundamental paper in '97. So his objection was his object was the following. So he was trying to give a framework for understanding TCP congestion control. And what's happening with TCP congestion control is that it's a protocol that was designed by Jacobson, the additive increase, multiplicative decrease, in a small network in the laboratory. And it was very successful there. Then it was ported onto the internet, which was very small in those days. And it grew and grew and grew. And the same protocol gracefully scaled all the way and allowed all this growth. I mean, had it not been for TCP, this massive growth wouldn't have been possible unless something equally scalable had been designed. Okay, so given this immense success of TCP, the question was, why does it work? You know, was it pulled out of the hat? Yeah, but is there some theory behind it in retrospect at least? And the answer is basically Kelly's model. In Kelly's model, these FIs will be source rates, and the prices of edges can be viewed as either probability of packet loss in TCP Reno or queuing delay in TCP Vegas. And now every unit of flow is either going along a path of least probability of loss or a path of least delay, right? And in this framework, Kelly established a very fundamental theorem that these equilibrium flows satisfy proportional fairness. So fairness is clearly a very important criterion in TCP, and probably the reason for its success, because it's not the case that few people can talk to each other and the rest of them are just twiddling their thumbs. Everybody gets a chance to participate in the internet. Everybody's traffic does get its chance, and he showed that some amount of fairness can be formally proven in this model. This is a rather weak notion of fairness, but still it is a notion of fairness. And actually Kelly's had a huge following, and people managed to prove the following very impressive theorem, that if you think of this primal-dual procedure where the primal process is packet rates as sources following Jacobson's additive increase multiplicative decrease protocol, and the dual process is random early delete following the Jacobson-Floyd protocol, then these two converge to the equilibrium in the limit. The equilibrium that is given by the convex program of Kelly, which I haven't specified yet, but I'll come to that. Okay. So going back to the old story, so after the semester at Berkeley, I was at Cambridge in the summer of 2002, and I gave a talk about our equilibrium algorithm, and I ran into Frank Kelly there, and Kelly and I realized that in fact his model, the one that I just stated, is really a generalization of Fisher's linear case. And so since Fisher's linear case had a combinatorial algorithm, we said, why not find combinatorial algorithms for his model, his resource allocation model. And then for 3 years, nothing happened until last summer, while Kamal was here at Microsoft and I was in Greece, and guess who was paying for the phone calls? We got a strongly polynomial algorithm for the case of single source multiple sink market. Okay, so let me introduce to you this new market. So here we are given a network with vertices, edges, and a single node called the source, and capacities on edges, and a bunch of sinks with the money specified, and we want to find equilibrium flows and edge prices. Okay, what does that mean? That means again the same conditions. We want to find flows and prices of edges, so that edges have positive price only if it is saturated. Flows always go on cheapest paths, and the money of each agent is fully spent. Right? So let me give you an example to show this. So we have one source and two sinks, and these are the edge capacities of the red edges, and the black edges have huge capacity. They'll never be saturated because you cannot send more than 4 units of flow because of this cut. And let's say that these edges are all of capacity 10. Then suppose that both of these sinks have $10 each. then the question is, what are equilibrium flows and edge prices? So turns out these are the equilibrium edge prices, $5 per unit of flow on both these edges. So that any path from source to this sink costs $5 per unit. So he should get 2 units of flow, and he should also get 2 units of flow. And indeed that happens. So 1 unit goes like that, 1 unit goes like that, and for the other sink 1 unit goes like that and 1 unit goes like that. And these are equilibrium flows and edge prices. Unique. Okay. Now let's do a small modification. Is it clear? What happened? So let's change this money of sink 1 from $10 to $120, so that he's going to dominate the market. He wants as much flow as possible, regardless of what he gets. Okay. But observe that he cannot get more than 3 units of flow, because 1 unit can go like this and 2 units can go like this. Okay. So his flow must cost him $40 per unit. And this is how it happens. These are the edge prices per unit of flow. And this unit of flow costs him $40. And this also. And then this guy can get only, well, the cheapest path to him is of course 10. Right? And he can indeed get his 1 unit of flow. And again you have all the equilibrium conditions satisfied. And this small change completely drastically changed the solution. Yeah.
Yeah, I require the sum of flow to be less than the maximum.
On what?
On each edge, I require the
Oh yeah. Flows have to satisfy capacity constraints, obviously.
the sum has to be less.
Yeah. I mean the usual, feasible flow conditions, right? Conservation at the nodes and capacity constraints. But but also satisfying the equilibrium conditions. Okay. So let me show you the algorithm that gives this these answers. Not only this is an acyclic graph, but our algorithm works for any graph. Okay. So this algorithm has a very simple description as an ascending price auction. And in this auction, the buyers are these sinks which come to the market with money, and they want to get as much flow as possible along cheapest paths. And the sellers are edges who want to get as much money as possible for their capacity. Right? So here's how the auction works. Okay. Just one simple point about auctions. So suppose I have k identical goods, like k identical laptops, Dell laptops with Microsoft software, let's say, and I want to sell them, okay, to this room, maybe 4 of these, okay. So I start with price 0 and everybody wants them, of course, and I keep raising the price and people keep dropping off because it's not worth it to them for, let's say, $300 or something. I keep raising the price, and at some point when there are exactly 4 people left, I stop and I give it to the 4 people, and that's the auction price, right? That's an ascending price auction. So let's see how we'll use it. So we have this graph with one source and multiple sinks, and monies of these sinks and capacities on edges. Okay, so what we do first is we find a minimum cut separating S from all the sinks, the source from all the sinks. Let's say it has capacity 60. Okay, now and let's say that we'll price all these edges of this cut at P. Okay, P is now, which means that the cheapest path from source to each of these sinks has cost P right now, right? And throughout the algorithm, what we'll do is we will define Ci to be the cost of the cheapest path from source to sink, Ti. Okay, Ci. is the cheapest path. And so sink Ti demands Mi divided by Ci amount of flow throughout the algorithm. And this Ci could be keep changing, and so therefore this could keep changing through the algorithm. So as I said initially, all these paths have cost P, right? All the Ci's are P, and every sink is demanding P. So when P is 0, every one of these sinks is demanding infinite amount of flow. So this cut is highly oversaturated. Okay. Now we start raising this P, and so the demand of all these sinks keeps dropping, and we'll do it like an auction, right? So we start with price P, and while this cut is oversaturated, we'll keep raising the price. And when this cut is exactly saturated, at that point, we will sell off the edges. So we keep raising this price P until we arrive at a price P naught, such that some other cut comes up here, say let's say of capacity 50, and some of these sinks are trapped on this side of the cut, and this particular sink demands exactly 10 units of flow at this price of P naught. Okay, is this getting clear or highly confusing? Clear? Okay, so good. So we raised this price until a new cut came up, let's say of capacity 50, and the sink that was trapped on this side demands exactly 10 units of flow at this price. If we raise this price any more, he will demand less than 10 units of flow. We cannot send more than 50 units across this cut, so that means this cut will be undersaturated, and these edges are really scared at this point, because if you raise the price anymore, their price will go down to 0. They will not earn any money for this particular problem, so they declare themselves sold at price P naught. Okay. Now at this point, however, this cut may be oversaturated because these things have a lot of money, and this cut may be oversaturated, and it's just demand is more than supply, so we need to increase the price here, and that's what we'll do. We start increasing the price of all these edges until some other cut comes up, let's say of capacity 20, such that these guys are now demanding a total of 30 units of flow, these two guys. And now if we raise this price anymore, this cut will not be fully saturated. So we declare this sold, fix the price here, and continue. Then raise the price of these edges. So that's the algorithm. And you could tell that it happened in strongly polynomial time, right? So I will not go into the implementation. Okay, if you don't mind, I think I'm running into time, so I will. Okay, so in any case, going back to the old story. So here's the Eisenberg-Gale program, the classic Eisenberg-Gale program that I mentioned. Yeah. 5 more minutes, but I started late, right? Sorry? Okay, that's better. Okay. So, so this is the Eisenberg-Gale program. What it's saying is maximize monies, the sum of monies times the log of the total utility of the buyers, where the utilities are these given by these linear functions. So it's maximizing this nonlinear objective subject to linear packing constraints. And you can show through KKT conditions that basically so the Lagrangian variables corresponding to these constraints will be prices of goods, and you can show through KKT conditions that optimal primal and dual solutions are in equilibrium. They satisfy Fisher's conditions of equilibrium. And amazingly enough, Cayley gave a very similar convex program for his market model. And this convex program captures equilibrium allocation, equilibrium flows for his market model. And again, this has the same form, maximize mi log fi, the flows, subject to linear packing constraints. Okay. And the amazing thing is that these algorithms which run in polynomial time, so our algorithm, which is primal-dual, gives shows that solutions are always rational to these nonlinear convex programs.
And the number of bits depends on only the size of the program, not on the bits of the...
No, the number of iterations depends only on n.
The number of iterations
To the algorithm. So assume the usual model that you can store log n size.
How do you express the final solution?
You will give equilibrium price and flows.
So the prices you have to specify bits.
Right.
How many bits?
They'll be log n bits long.
So they do not depend on the number of bits being...
No. Oh, no. So you assume your usual model, okay, whatever is the size of your input bits, that doesn't grow up. Yeah.
What about these epsilon approximations for
Right.
covering acting?
So yeah, I'll come to approximations. So I'm right now in the think of this as the 1950s and 60s of primal-dual, okay, applied to non-convex programs, okay, and we still have to get to 1990 when approximation algorithms happened. Okay. So just to say, so in our convex program, in our algorithm, the primal variables are flows, dual variables are price of edges, and we do these alternately, flow and the flow and price updates in the primal-dual fashion. Okay, so this was a big boon for us across continents, and we said, okay, since two of these Eisenberg-Gale-type programs have rational solutions and yield to polynomial time algorithms, how about more? And then we said, okay, why does this algorithm really work out? Well, the big reason behind it, of course, is actually the Maxwell-Minkert theorem. Okay, but then we started looking at more general versions of Kelly's problem, and we soon realized a big problem. Namely, for two sources and three sinks, we already run into irrationality. So if you have one source and two sinks for this source, and another source with one sink, and $1 for each of these sinks, and these capacities are 1 and 2, then the equilibrium prices are irrational. So we cannot expect a combinatorial algorithm of the time that I gave earlier for this problem. And as I said, Maxwell-Minkert theorem is at the heart of that algorithm, and there's no such theorem for this kind of a setting. So we look for other settings that have Maxwell-Minkert theorems. And here are some other settings to consider. Two source sink pairs when the graph is either directed or undirected. The branching market rooted at sources. So what is this market? So say you have a directed network with capacities on edges and a bunch of sources with monies, and you want to find branchings rooted at these sources. So this is a branching rooted at S2, this is the branching rooted at S3. Okay, so you want to find a packing of branchings and edge prices so that only saturated edges have prices. Every branching is the cheapest possible at that source, and all the monies of every source is fully used. And again, not surprisingly at all, there's an Eisenberg-Gale-type convex program that captures this market completely. Optimal solution to this program is equilibrium branchings for that market. So, yeah.
You ever say why that's
KKT conditions. Excuse me. So, here are these markets, and then at this point, what we did was we defined the notion of an Eisenberg-Gale convex program, which is basically maximize this kind of an objective subject to linear packing constraints. and defined the notion of an Eisenberg-Gale market as any market whose equilibrium is captured by the optimal solution to such a program. And we said, which of these markets have strongly polynomial algorithms? Okay, and we found these strongly polynomial algorithms for these markets. Two sourcing pairs, undirected graph, due to a Max-Floor-Mincutt theorem of T.C. Hu, spanning tree market due to Nash-William-Tutt theorem, two sources branching market due to a Max-Min theorem based on Edmonds theorem and something more that we had to do. And then we showed that the three source branching market is irrational, so it doesn't support polynomial time algorithms. And then there were these two markets, two sourcing pairs directed graph and another market for which we knew there were no Max-Floor-Mincutt theorems and we couldn't get irrational examples either. Okay, but earlier this year, together with two students, Chakrabarti and Devanur, we showed that these markets are also strongly polynomial. Okay, and if I have 3 minutes, I can show you the algorithm. I have 3 minutes. Okay, okay. So let's do the following. I will go to the punchline and come back to the algorithm if there are people. Oh yeah. So stick around if you want to hear this algorithm, and that's the nice pictures that happen. So it's LP based. So there's no Max-Min theorem, but things work. Yeah. And strongly polynomial also. I told you it's strongly polynomial. Okay, so here's the summary of what happened. So here's Eisenberg-Gale markets, and this is submodular utility allocation markets. I didn't define that. All of these are rational, and this is Eisenberg-Gale markets with two agents, the second work that I talked about. And here are some of the markets that I talked to you about. And surprisingly rich set of possibilities here, and it gets even more interesting once we look at the notion of efficiency of these markets, which is like the price of, the price of anarchy, right? So this is like the price of capitalism, and we can define efficiency as, the worst equilibrium utility, total equilibrium utility achieved divided by max utility. And again, it gives a rich classification. Here are efficiencies of some of these natural markets. And then we study fairness also in these markets and something else called competition monotonicity. And just to cover Cepheus problem, we need basically we need to look for strongly polynomial algorithms for approximating these nonlinear convex programs and run primal-dual in an approximate setting. I don't have any clue how to port all that exact stuff to the approximate setting. And even in the world of LPs, it took some time to go from exact setting to approximate setting through relaxed complementary slackness conditions. So what's the equivalent thing to happen here? I don't know. And also this could lead to some more insights to congestion control protocols. And the structure of these markets is still wide open. There's lots of open problems still left. As you can imagine, these are only very, very few pieces of a very, very large puzzle. And what it will look like eventually, I don't know, but in a few years we'll find out. Thank you.